On a calm, sunlit morning in Hawaii, something unexpected happened. Without warning, the ground shifted. In just minutes, entire sections of land moved nearly 8 meters. The coastline dropped. The ocean surged inland. A powerful magnitude 7.7 earthquake struck the south side of the Big Island. But there was no dramatic volcanic eruption, no lava fountains lighting up the sky. This wasn't an explosion, it was the island itself, slowly sliding toward the ocean. And here's what makes this even more unsettling. That movement never truly stopped. Today, highly precise GPS instruments show that the southern flank of Kīlauea Volcano is still creeping toward the sea, pushed outward by magma rising from deep below. Even more concerning, ancient geological evidence reveals that massive landslides have happened here before. If it happens again, the ocean won't wait. A tsunami could reach Hawaii's shores in minutes. So the real question isn't whether the island is moving, it's how far the next shift will go. When most people think about Hawaii, they picture glowing lava, black sand beaches, and rivers of molten rock flowing into the ocean. They imagine eruptions rising upward, dramatic and visible. But volcanoes don't just grow upward, they also spread outward, and sometimes they fail sideways. On the southeastern side of the Big Island, along the slopes of Kīlauea, an enormous section of land is slowly shifting toward the Pacific Ocean. Scientists call this unstable region the Helena Slump. This is not a small crack or a narrow fracture you can step across. It is a massive portion of the volcano's southern flank, stretching from high on the mountain, across the coastline, and far beneath the ocean's surface, descending thousands of meters below sea level. It's not the entire island that's unstable, but the section that is powerful enough to reshape the coastline if it suddenly moves. Kīlauea itself was built over hundreds of thousands of years by a deep mantle hotspot, constantly pouring out lava onto the Pacific plate. Layer after layer of hardened basalt stacked up, forming a massive volcanic structure. But as the volcano grew, it also became incredibly heavy. That weight presses down on the oceanic crust below, crust that is already bending under the mass of the entire Hawaiian island chain. Beneath the south flank lies something critical, a nearly horizontal detachment fault, a weak, slippery boundary that separates the volcanic rock above from the crust below. Magma rising inside the volcano pushes the flank outward, while gravity pulls it toward the sea. From the surface, everything feels solid, stable, permanent, but deep below, the entire slope is slowly moving. Beneath Kīlauea, pressure is always building. Magma rises from deep within the earth and forces its way into cracks known as rift zones. As it pushes into these magmatic, it forces the surrounding rock apart, slowly driving the volcano outward from within. Each pulse of magma increases internal pressure, and that pressure has to go somewhere. When magma intrudes into the eastern or southwestern rift zones, it pushes directly against the south flank. The movement is subtle, but measurable. GPS stations anchored into the ground show that this flank moves more than 5 centimeters toward the ocean every year. That may not sound like much, but over decades it adds up to meters of movement. And this motion isn't constant. It speeds up during eruptions when magma pressure increases. It slows down during quieter periods, but it never completely stops. The south flank is directly connected to the volcano's internal system. As pressure builds below, the alard above adjusts. Most of the time, the movement is too slow to notice. But deep along the buried detachment fault, stress continues to build. And eventually, that stress has to be released. On November 29, 1975, it was. The south flank of Kīlauea suddenly slipped. A magnitude 7.7 earthquake ruptured along the detachment fault beneath the volcano. In just minutes, parts of the Helena Slump shifted up to 8 meters toward the ocean. Sections of the coastline dropped, cliffs fractured, and almost immediately, the ocean responded. A tsunami surged along the Hawaiian coast, with waves reaching over 10 meters in some areas. 2 people lost their lives, boats were torn from their moorings, infrastructure was damaged, the island itself had moved, but here's the most important part. This wasn't a total collapse, it was a partial release. The built-up stress was discharged, but the system didn't fail completely. It adjusted, And then it continued. After 1975, the south flank did not stabilize. It kept moving. Magma continued to rise. Pressure continued to build. That event proved something critical. The Helena slump is not theoretical. It's not just a model or a possibility. It is an active, moving structure capable of sudden, powerful shifts. And it is still connected to a living, breathing volcano. Today, nearly 5 decades later, the movement hasn't stopped. Modern GPS systems, far more advanced than those in the past, show that the south flank is still creeping toward the ocean at a rate of about 5 to 10 centimeters per year. This slow motion is driven by the same forces as before, magma pushing from within and gravity pulling downward. In 2018, during a major eruption of Kīlauea, a magnitude 6.9 earthquake caused the flank to shift again, this time by nearly 2 feet. Instruments recorded measurable movement toward the sea. This confirmed something scientists had long suspected. The movement of magma and the motion of the flank are directly connected. The detachment fault beneath the volcano is not isolated. It responds to changes inside the volcano. As stress builds along that fault, it can be released suddenly in the form of earthquakes. From the surface, everything may look calm, but beneath that calm, the system is active, slowly, constantly, building toward the next shift. Which leads to the most unsettling question of all. What if a much larger portion of the south flank suddenly collapsed? If a massive section of Kīlauea were to break free and slide into the ocean, it would trigger a huge underwater landslide, and that movement could displace an enormous amount of water. The result? A tsunami far larger than the one in 1975. Early simulations suggested that waves near Hawaii could reach extreme heights, with energy spreading across the Pacific Ocean. Some models even projected waves reaching distant coastlines thousands of kilometers away. The idea is difficult to ignore, a massive wall of water racing toward shore, overwhelming everything in its path. And there's a reason scientists take this seriously. The seafloor around Hawaii contains clear evidence of ancient collapses. Huge debris fields show that massive sections of volcanic islands have broken away in the past. These were not small events, they were enormous geological failures that reshaped the ocean floor. So yes, it has happened before. However, modern research offers a more detailed understanding. The south flank doesn't appear to be one single solid block ready to collapse all at once. Instead, it is likely divided into segments. These segments move gradually, slipping in stages rather than failing in one catastrophic event. But that doesn't mean the danger is gone. Large earthquakes, magnitude 7 or even 8, are still very possible. During these events, sections of the coastline can suddenly drop. Local tsunamis can still form. Waves over 10 meters high could strike parts of Hawaii with little warning. Even without a total collapse, the risk remains serious. The system doesn't need to completely fail to cause destruction. It only needs to slip. The good news is, this region is closely monitored. Scientists use GPS stations to track movement down to the smallest atophyseal. Seismometers record earthquakes deep beneath the surface. Satellites scan the alarm from space, detecting even tiny changes in elevation. Every shift, every movement is being tracked in real time. Hawaii also has tsunami warning systems, evacuation routes, and emergency plans based on past events. The lessons of 1975 are still shaping how the islands prepare today. But even with all this technology, there's one thing we still cannot do. We cannot predict exactly when the next major shift will happen. The south flank is still moving. Magma is still rising. Stress is still building. The system is understood, but it is far from quiet. And while instruments can measure every centimeter of movement, they cannot tell us when the next big release will come. Deep beneath the surface of Hawaii, the island is still slowly sliding toward the sea, and one day it will move again,